All right, so your second exam is coming up for dynamics, and I wanted to take this time to kind of talk about a little bit what's going to be on it, kind of review what you may see, the topics that'll be on it, good things to note and remember. Where this exam kind of has an interesting mixture of content because it's going to have both chapters 15 and 16 on it. And chapter 15, where we had that one, was still back in our kinetics of a particle. So that was kinetics of a particle, specifically impulse and momentum. Right, so this exam is only going to cover content after the first exam. It's not necessarily cumulative. It's really going to be just over chapters 15 and 16. This kinetics of a particle, specifically on our impulse and momentum subjects, but then also is going to be over chapter 16, where we've been talking about these planar kinematics. So we've been talking about planar kinematics of rigid bodies. So I think one of the tougher things that you'll have to do in this exam is discern whether you're looking at a particle problem, like whether you can analyze something as just being like a single point, treating it like a particle, a point in space, versus do you treat it like a full body, right? Is it a point or is it a full body that you have to treat it as? And so we'll kind of talk about some of the topics for each of these that would be good to know, good to remember. And so we'll start with chapter 15 here, that kinetics of a particle, impulse and momentum. I'm not going to tell you like explicitly to use impulse and momentum or like use this formula, do it in this method. It's totally acceptable if you solve a problem using another method. Like if you get a problem that you can treat like a particle and you solve it using work and energy, or you solve it using F equals ma, that's totally acceptable to me. I won't ask you for a specific method of doing something. It's just that the problems that I give you are probably going to be skewed to be a little bit easier if you do impulse and momentum kind of methods. So if you remember from our impulse and momentum, one of the big ones that we had talked about was the principle of impulse and momentum. Principle of impulse and momentum. And that was where we took the summation of all of those impulsive forces. So integral from T1 to T2 of F dt equals our final momentum minus our initial momentum, which is our mass times velocity. Right, so we worked a few different problems where really the benefit of this principle of impulse and momentum was if we had forces, velocities, and times. Because usually, you can do, if you're given accelerations, it's a little bit easier to use F equals ma. If you're given velocities and positions, it's a little bit easier to use work and energy. But when you're given times, it's a lot easier to use this principle of impulse and momentum. So those were a lot of the examples that we had worked with this equation. And we also did conservation of momentum, right? So we said if there are no impulsive forces, and impulsive forces are anything that like aren't conservative forces. So if you have things like friction, times where things are like external forces, like general external forces, somebody pushing something, in those cases you would have to use impulse and momentum. But if there are no external forces, then you can use conservation of momentum, which is the sum of all your masses times velocities initially. It's going to be the sum of all your masses times your velocities final. And along with that, we also talked about impact. So impact was a special case of this. where we use the coefficient of restitution, that lowercase e, of VB2 minus VA2 over VA1 minus V1. We use this coefficient of restitution when things are impacting each other and bouncing off each other, but they're losing some energy in there. So that's what our coefficient of restitution is representing in that. And we saw generally two kinds of impact problems. We either had central impact, where two objects were kind of on the same line of action and impacting each other directly, or we had oblique impact, where we had one maybe coming up at a different angle than the other one. Okay, so they might be coming up at different angles and kind of interacting a little bit differently in that way, giving us two components, like an x and y component, instead of just being on the same axis impacting each other. So understanding kind of how those are different, and how the applications of central impact versus oblique impact have a little bit different procedures in them, a little bit different rules between the two of them to figure out what those initial and final velocities are. And then finally, come bring this all the way down here. Finally, the last thing that we had talked about was angular momentum. Angular momentum. And with that angular momentum, the principle, or I guess our main topic with angular momentum was the principle of angular impulse and momentum. And the big difference with that one is that we said, you know, this is going to look a lot like our principle of impulse and momentum. Our principle of angular impulse and momentum is essentially just multiplying everything by r, multiplying everything by a radius. So we had taken, instead of having this f dt, we had summation of moments. Summation of moments. Sorry, integral from t1 to t2 of all of our moments dt equals our final angular momentum minus our initial angular momentum, where our angular momentum h is r cross mv. Right, so just that radius cross product with our regular momentum of mass times velocity. And our moments we could also relate with forces, because our moment is our r cross f. Right, so we could do that cross product with forces to find moments there and relate those back. So that angular impulse and momentum, typically for objects that are undergoing rotation, right? And this rotational movement was kind of a lead-in and a transition into talking about all of this angular velocity and angular position and all of this rotational stuff that we've been doing now lately for the last, couple of weeks in this chapter 16 as we're talking about planar kinematics. So those are all of the topics that we had covered before we transitioned to talking about rigid bodies. Right, so you could see any of these topics of impulse and momentum in our exam. And then the other big topic that we've been talking about a lot lately is the planar kinematics of a rigid body. So with that, what we've seen is basically the three modes of motion that we've talked about for planar kinematics. So the first one is translation, which is where the body, it just moves. It either moves rectilinearly or curvilinearly, but it doesn't rotate. It just moves. Everything is in line with respect to itself, like a car on a Ferris wheel, right? A car on a Ferris wheel moves in a circle, but it always stays upright. And we hadn't actually worked any problems with translation because the key to translation is that you can treat it like a particle. So we hadn't worked any problems because we had essentially just been treating everything like a particle so far in this entire class up until this point. So that's the only thing to know with translation. If you see some kind of translation problem, you're just treating it like a particle. The bigger topics that we talked about were rotation about a fixed axis and general plane motion. So we talked a lot about rotation, about a fixed axis. And this is where we had introduced all of our theta for our displacement, angular velocity being the derivative of that theta with respect to time, angular acceleration being the derivative of that angular velocity, or the second derivative of that displacement with respect to time. And so we had talked about kind of the general kinematics of all of these, using these derivative relationships to get between velocity and acceleration, using the constant acceleration relationships that we sometimes saw. So like omega equals omega naught plus alpha t. Right, just exploring all of those relationships of that rotation about a fixed axis, kind of translating those position, velocity, acceleration relationships that we had seen for particles, translating them to rigid bodies, translating to them to this angular form. I'll write out all of these equations for our constant acceleration. So this is constant alpha for these right here. So theta equals theta naught plus omega naught t plus 1/2 alpha t squared. And our last one, omega squared equals omega naught squared plus 2 alpha theta minus theta naught. And then we also translated these back and forth between our like linear position, velocity, acceleration to our angular velocity, position, acceleration, all of those, where we said ds equals r d theta to get between our different positions. Velocity is angular velocity cross product with the radius or position vector r. Tangential acceleration is angular acceleration times r. Normal acceleration is omega squared times r, and we can put those together for acceleration equals alpha cross r minus omega squared r for rotation about a fixed axis. So it was really applications of all of those different equations, all of those relationships together. And then we had one special case in our rotation about a fixed axis, and that was gears and gear ratios. So understanding gear ratios, how those are used, when those are used. Gear ratios, where the most common gear ratio you commonly see is omega A times RA equals omega B times RB. But just knowing you can use accelerations here instead, but you have to use those angular kinematics, those, alpha A times RA equals alpha B times RB, to move from one gear to another with those gear ratios. And then finally, and maybe our biggest and most difficult probably topic, is our general plane motion. And what we had talked about in general plane motion was essentially we had two different ways to find velocities, and then we also had acceleration. Okay, so in our general plane motion, we talked about how to find velocities using relative motion. And we did that with this VB equals VA plus omega cross RB with respect to A. And so we split everything up into vector form. We found this relationship, and then we were able to solve for, angular velocity or velocity of B by breaking this up into Cartesian form, breaking out the i's and the j's separately as two equations, and then solving. And we had a very similar setup for acceleration, right? We did a relative motion of acceleration too, where we had acceleration of B equals acceleration of A plus alpha cross RB with respect to A minus omega squared RB with respect to A. And so that was the exact same kind of procedure, breaking things up into Cartesian form, putting those vectors in, separating out i's and j's, and then solving for your unknowns. The other, and I've kind of run out of room here. Don't know. See if I can just move all that up a little bit. Yeah, that works. That's fine. The other method that we had was what we called instantaneous center of zero velocity. Instantaneous center of zero velocity, and this was an alternative way to find velocity. So you can either use relative motion or instantaneous center of zero velocity, where the benefit really is like you can do both ways and check yourself, right? That would be the main benefit for knowing both ways for this exam, because I won't ask you to do one way or another, but it's a really good way to check yourself, to know if you're on the right track or not. And with those instantaneous centers of zero velocity, you're taking the, if you have like a velocity of A and a velocity, let's say, maybe here's velocity of B, you're essentially taking the perpendicular, a vector that is perpendicular to both of them, finding where they intersect, and that is your instantaneous center of zero velocity. And then you create a triangle that relates these together so that you can find those vectors. So you can use scalar relationships where VB equals omega RB with respect to IC. Right, so you can use scalar relationships there when you have these, when you have those vectors figured out, where this is your RA with respect to IC, RB with respect to IC for those instantaneous centers of zero velocity. So just another way that you can solve those. And then the very last thing that we had seen was kind of a special case in all of those, and that was rolling without slipping. Right, so just know that that is another case that may come up. We saw it with our relative motion problems, the rolling without slipping. And I think the main equation there is VG, which is the center of your object that's rolling. VG is omega R. So that's for rolling without slipping problems. And AG is alpha R. Right? AG is alpha R. for those rolling without slipping problems. So you could see any combination of those for this exam. I am not 100% sure what the question split will be on this. It will still be 3 questions. And I think it will probably be 2 from chapter 16 and 1 from chapter 15. I'm not 100% sure on that yet. It could be the other way. It will definitely be 1 of each for sure. Like 1 of 15, 1 of 16. And then it is likely going to be 2 from 16. If I had to get. I haven't written the exam yet, so I'm not entirely sure. But I think this is the split I'll probably go with on our exam. Unless you get lucky, I guess. This 15 I think is just a little bit easier. Maybe a little bit more comfortable for you. But that's going to be our general split. It's just going to be these 2 chapters of everything that we've covered since exam 1. And of course I'll have office hours, and I'll have our practice exam up through the Pearson or Mastering Engineering, and a solution key on our D2L up pretty soon. So use those as study tools. I always say the practice exam is always your best study tool. I know it's really long, and I know it's really painful, and you think it's really dumb, but practicing those problems, just doing those reps over and over again, it's just like going to the gym. You just have to keep doing the same boring motions over and over again to get better, right? It's the same thing. It's the only way you're going to build this muscle is by practicing the movement over and over again, practicing those reps, understanding the problem and what's happening so that you can figure out what your approach needs to be and how to tackle a problem in the short amount of time you're given for an exam. So best of luck with all of your studies, and let me know if you need anything.